high TC superconductor lanthanum strontium cuprate doped with neodymium, frustrated magnet indium copper vanadate with stoichiometry 239, and also lanthanum and neodymium baphonates that also can be considered as scintillation matrices. So, and I divide my report according to these three directions, and let's start from the lanthanum strontium cuprate. So the structure of LSCO consists of alternating layers of copper or two planes with lanthanum polyhedral layers. And copper or two planes is a key structural unit for obtaining the superconductive properties in this material. And these superconductive properties appeared when this plane doped with some charge carriers. For instance, the holes that formed with substitution of lanthanum with divalent strontium atom. Additionally, we can substitute lanthanum in a lattice with a neodymium ion to create some such called effect of chemical pressure that strongly influences of the TC value. And if we take a look on a phase diagram for the LSCO, we can see that with increasing of the whole concentration in a compound, the LSCO goes from the antiferromagnetic insulator to the metal. And somewhere in between, in an optimal doping of the holes, we have the region of the superconductor. And above the superconductor property, we have the so-called pseudo-gap phase. And interesting that properties for the LSCO doped with neodymium in the optimal concentration of the strontium. So it's from 0.5 atomic persons of the, from 5 atomic persons of strontium to the 15 atomic persons of strontium. The properties of this compound is studied, but as we work with the matrices with concentration of strontium 90 atomic persons, we go from the so-called we go to so-called overdoped regime where the properties of the compound not so understood till now. So it was interesting to understand how the neodymium content influences the properties of these matrices. And as you can see on a binary diagram that representing the state of the binary system depending on the ratio, you can see it on a X scale in a temperature. The lanthanum cuprate melts with decomposition. And obviously that this material in a single crystal form can be obtained with a classical melting technique. So in such a case, we use a so-called traveling solvent floating zone that can be schematically represented like we use the feed with composition beta that equal to our goal compound. You can see it on a phase diagram. We attach some kind of a solvent. Solvent usually choose from the composition relevant to the liquidus line below the peritectic point, this one, the decomposition of our compound, and above the eutectic point. And this solvent form the, oops, sorry, yeah, form the melting zone. And during the growth, our gold composition from the feed solute in a melting zone and afterwards crystallizes on a seed. And here you can see the growth facility. So this is the mirrors for that focused the light from the halogen lamps to create the heated zone. And this is how the growth looks in reality. So this is the feed, our gold compound. This is the melting zone, our solvent, and this is seed with a grown crystal. So from literature, it's well known that the necessary parameters for the growth of the LSCO compound without doping of neodymium. So these parameters is solvent composition, growth rate, rotation rate, and atmosphere. And the postdoc from our department that worked before me about this in this project, he tried to obtain the LSCO with neodymium in this regime of overdoping. And obviously that he used the same growth parameters that can be found in the literature. And as you can see, the crystals have a lot of voids and cracks on a cross section. And from the shape of the crystal, we can say that during the growth, we have a lot of overspilling of the melt. And my first experience was carried out with the same parameters of growth. And as it can be discovered, the low pressure of the oxygen leads to the creation of the bubbles in a melting zone. And when we have such bubble in a melting zone, it influences the shape, as you can see from these videos. And usually such presence of the bubble leads to overspilling, obviously, and to the tilted growth of the crystal due to the of axis rotation of the feed rod and the seed with a growing crystal. So as the increase of the pressure in the growth chamber can be a tool to prevent of this bubbles formation in the melting zone. And as you can see from the comparison, with increasing of the oxygen pressure in the growth chamber and with decreasing of the growth rate, we obtain the crystals of high quality with sufficiently big crystalline part of the single crystal. And as you can see, crystals present the observable effect of the grain selection in it. And in crystal, there was no voids or cracks were detected. And XRD results prove that in our samples we obtain the single phase of the LSCO doped with neodymium, and lower pattern confirm the creation of the sufficiently big and defect-free single crystal grain. And for more precise analysis of our crystal, we use EDX analysis of the grains, of the single crystal grains. And as you can see from the result, we obtain the EDX analysis proof obtaining of the LSCO doped with neodymium phase. And as a conclusion for this part, I can say that using of another growth parameters such as higher oxygen pressure in a growth chamber and lowering of the growth rate can prevent the spilling of the melt during the growth, cause the stable growth of the crystal, and leads to obtaining of the crystals of the high quality. So now let's talk a bit about vanadate with stoichiometry 239. So this is again the composition compound with a layered structure where the magnetic copper ions are arranged in a honeycomb structure with vanadium ion in the center of each hexagon, and this layer altering with indium O6 polyhedral. And the main problem with this compound that it can be obtained, still can be obtained in a single crystal form because it again melts with decomposition, with decomposing. And according to the mm, three ternary phase diagram between copper oxide, indium oxide, and vanadium oxide, um, we obtain in this system two different mixed vanadates with different stoichiometry, 115, and our goal compound 239. And this, interestingly, that this copper vanadate with stoichiometry 115 melts incongruently too, but it melts at lower temperature than our gold compound. And as a solid product of the melt, we have our gold compound 239. So the first approach for obtaining of the gold compound was just a melting of this compound with another stoichiometry. So the process was carried out in a high temperature optical microscope. So the crucible, aluminum crucible was placed in a quartz tube here. Then it was going up to this chamber with that works just similar to the floating zone furnace. There we have the lamps and the mirrors to create the melting zone. Here we have the camera to observe the process, and we receive a picture on the computer of this. So the process was carried out in air atmosphere. The temperature and the dwelling time you can see on the slide, but the only thing that as a raw material we use only stoichiometric mixture of the starting oxide, and as a result we obtain such a batch, and XRD result for such batch prove that in the end we obtain just a mix of different compounds. So such approach appeared to be not so successful for obtaining our gold compound. So the next approach, it can be a flux growth of this composition. And usually we use as a flux oxides, hydroxides, salts, or eutectic binaries of the salts. Eutectic binaries is such an interesting composition of the two compounds that have the melting points lower than the melting points of the initial salts. But the main problems with such usual classic, let's call it like this, flux, is that after growth, ions from the flux can incorporate in the lattice of the gold compound. So the next step was to find the so-called self-flux for this composition. So this is eutectic binaries between oxide that included in our system. And as you can see from the binary system for the copper oxide and indium oxide, below the temperature 950 degrees, there is no liquid phase was determined. And interesting that in the binary system between copper oxide and vanadium oxide, we obtain two different eutectics that quite good for usage as a self-flux. And we use in our experiments the eutectic 2 as a self-flux. The composition you can see on a slide, and the growth process was carried out like fast heating, then holding for the proper time at temperature, then slow cooling down to promote crystallization, and rapid cooling to the room temperature. And as you can see, after the experiment, as it was carried out in alumina oxide crucible, all the crucible and even plates that was situated under the crucible was totally soaked with the flux, and it so it means that such crucibles are not sufficient for such experiments. But interesting that we still obtain some crystals, and XRD analysis for these crystals uh, showed that we obtain mixture of indium vanadate and copper pyrovanadate in it. So the next step was preventing of interaction between our melt and the crucible. So we use the platinum crucible, again the same composition, but the only change in this experiment was that after slow cooling to the temperature of 800 degrees, we just switch off the furnace and then just decanting the flux at room temperature, but the mixture was still hot. And we obtained the crystal, good faceted, just slightly decorated with a flux. And XRD analysis proved that this was pure indium vanadate. So now let's move to the final part about lanthanum and neodymium gafnates. Structure of these compounds strongly depend on the ratio between rare earth ion and gafnate ion, and we are strongly interested in a hafnates with a pyrochloric structure, where the rare earth atoms sit in a 3D network of corner sharing tetrahedron. And for such materials, also the scintillation properties was studied, and as you can see, the properties is not so good. The light yield is very low, but the main advantages of this material is a high density, and that is quite and high Z effective, that is quite necessary for detection of particles with high energy, and sufficient value of band gap. So this material can be doped with different rare earth atoms. But the main difficulties with obtaining of these rare earth gafnates is that, first of all, they have very high, extremely high melting points, uh, about 250, about 2500 degrees. And the second problem that for some of the rare earth hafnates, the pyrochlore structure is decomposing, so we can't obtain it from the melt. Or we need to use some special technique for growth. So at the moment, what we achieve, we have the proper procedure for obtaining of the raw material of lanthanum and neodymium hafnates with a high content of the main phase, and traces of the starting materials not exceed 3 or 5%. And what is planning to be done in the future? There's the growth of LSCO crystals with neodymium content 0.3 and 0.4, and I showed you what is already done. This was the first trial for the LSCO growth with neodymium content 0.3. The growth finished last Friday, so it's freshly obtained, and as you can see, we obtained quite sufficiently long part of the single crystal grains in this crystal. So the second is a repetition of the melting copper indium vanadate with stoichiometry 115. So we have some ideas how to improve this. So instead of using the stoichiometric mixture, I'd like to try the pre-synthesis of the single phase and then try to melt it. Maybe something we obtain interesting. And growth of lanthanum and neodymium gafnates in crystal by flattening zone method. And last but not the least, I'd like to say thanks to all the people from Germany, from Ukraine, without whom this scholarship and this work wouldn't be possible. So thanks for your attention.
Thank you, Olesia. Are there questions from the audience on site or online? That's okay.
No, didn't measure it yet. Yeah, we just we obtain we already cut the sample and now it's under measurement. I suppose that I couldn't say does it.
Yes. From previous results from Kaushik, they are superconducting. But of course, yeah, a little bit lower, but we have to look also if maybe there's some oxygen annealing necessary.
Oh, okay.
So I have a comment maybe for the indium copper vanadate.
Yeah.
If it's possible to obtain polycrystalline material, if it would be interesting to try some kind of numerous grain growth technique to try to improve the grain size and get maybe at least microcrystals, something like this.
Oh, yeah. Yeah, thanks.
Do we have further questions online? If not, thank you, Olesia.
Thank you.